So, in the previous class we have seen the background for the nonlinear EIS. Okay. We have seen that if you apply large amplitude perturbation, you can get higher harmonics. When you measure the impedance, that impedance will depend on the perturbation amplitude. Okay. If you give a small EIC 0, the impedance will be independent of the amplitude. If you give a large EIC 0, it can change. Okay. And if you give large enough, it will definitely change. In order to understand or analyze this correctly, we need to have good mathematical background. Specifically, we have to have background in Taylor series expansion, in Fourier series expansion, and in special functions, one type of special function called modified Bessel function. Okay. I want to give a very brief introduction to the data acquisition. Okay. Later we will see detailed information on what we should do to get good quality data for nonlinear EIS. In the beginning, I just want to give you a very quick or brief introduction, and then we will move on to calculating nonlinear EIS for a simple electron transfer reaction. At a later stage, we will go for reaction with adsorbed intermediate, we will go for more complex cases where solution resistance plays a role. So, right now we will start with this simple electron transfer reaction. Okay. So, you have a potentiostat which is connected to the cell. You have to apply a sinusoidal wave. So, we can apply a sinusoidal potential using what is called a function generator, and that potential can be added to any DC bias that we want to give in the potentiostat, and you can get the current. It is a good idea to measure both the potential that is applied onto the cell and the current that is measured from the cell. Okay. We want to apply a DC bias and a AC potential, sinusoidal potential, but we want to also make sure that the applied potential is actually correct. Okay. So, the current that comes out, it can be subjected to Fourier series analysis. There are different ways of doing it. One method is to convert that current using an analog to digital board, it is called A to D, and then use Fourier transform in the software. That is, take the current values as a function of time and then subject that to Fourier transform. Another method is to use a hardware Fourier transform analysis, that is, when it is measured at that time itself, subject it to Fourier transform within the hardware and then just get the Fourier coefficient. Another method is called phase sensitive detection, in which case you multiply this by a sine wave. This can be done after digitization, it can be done in the analog domain itself, and then find out the component at omega or at 2 omega, whichever frequency we want to look at. Okay. So, that is using what is called lock-in amplifier. It can be done within software, it can be done in the hardware, either using FFT analyzer or using lock-in amplifier. Of course, if you want to do galvanostatically, it is possible to do, provided we give a DC bias if necessary, we give a DC bias and a sinusoidal current, and then measure the potential and then subject it to any one of these techniques. Now, I want to start with a reaction which is redox reaction. Fe2 plus is oxidized to Fe3 plus, and with the release of electron, we are going to assume that there is no mass transfer limitation, that is, it is a rapid mass transfer. Concentration of these two species are constant. Under that condition, we can write the Faraday current as F K1 concentration of Fe2 plus. Of course, K1 is the forward rate constant, K minus 1 is the reverse rate constant. We can also write it as Kf and Kr, Kf minus K reverse Fe3 plus concentration. And of course, each of these rate constants are going to be written in terms of potential for forward reaction as well as the reverse reaction. Now, total potential is DC plus AC, and rate constant value at the DC potential I can write it as Kf DC and Kr DC. So, when I expand this, I would get an expression saying F multiplied by Kf DC exponential of Bf EDC with the concentration of Fe2 plus, and correspondingly for the reverse reaction. and AC is given by AC 0 amplitude and the frequency omega, and we want to write this Faraday current in Fourier series as I 0 corresponding to the constant term, I 1 which is the magnitude of the response at fundamental with phase phi 1, I 2 is the magnitude of the response at the second harmonic with the corresponding phase psi 2, and so on for any of this. Now, exponential of A sin theta, we know it can be written as an infinite series in the modified Bessel function. It is actually a generating function. Likewise, for e power B f EAC 0 sin omega t, we can write in terms of the modified Bessel function at I 0, I 1, I 2, I 3 etc. And similarly, we can write it for the reverse reaction. So, you have a fairly large number of terms, but we will look at first few terms. Okay. If we want to look at the DC component of this response, if you look at this, you can separate this as the one corresponding to the forward reaction, one corresponding to the reverse reaction. For the forward reaction, you have Faraday constant, rate constant at DC potential, concentration, these are all fixed numbers for a given DC potential. This is the only constant coming out of this expression, and for the reverse reaction, the first term is the one that is a constant. So, I can write it as Faraday constant Kf dc Fe 2 plus multiplied by I 0 evaluated at Bf EAC 0, and correspondingly for the reverse reaction. In case of the response at fundamental, which we are denoting as IFAC at omega, case of response at the fundamental, it is going to be at sin omega t, which means m has to be 0, here also m has to be 0. When m is 0, we are going to get these terms and 2 I 1. So, I have taken the 2 out of this, 2 I 1 Bf EAC 0 minus here also Kr dc Fe 3 plus 2 I 1 Br EAC 0. At second harmonic, you can correspondingly find it is going to be cosine, third harmonic it is going to be sine, but then it will come with a negative sign, and so on. You can do it for any harmonic. Now, if I measure the impedance, if I give a large sinusoidal potential, but I just use a traditional or normal equipment and measure the impedance, I am going to get EAC 0 by IFAC at omega. So, it is going to subject that to Fourier transform, get the response at fundamental, take the magnitude and divide to get the magnitude of the impedance. Here, because it is sin omega t, the phase difference is 0, therefore, we are going to look at it as a simple resistor. The expression we get is EAC 0 by the entire IFAC at omega. Now, what happens when EAC 0 goes to 0? That is, when we use small amplitude perturbation, we should get the same expression as what we got before with linearization. So, limit of x tending to 0 I 1 x is going to be x by 2. Instead of x, we use Bf EAC 0. We are going to get Bf EAC 0 by 2. This multiplied by 2 will give us F Kf dc Fe 2 plus concentration Bf. Similarly, this side 2 I 1 Br EAC 0 will come to just Br EAC 0. So, these 2's will cancel out, EAC 0 will cancel out, and you will get an expression that is the same as what you got after linearization. So, certain points I would like you to note. One is the Faraday impedance is a constant at a given DC and at a given EAC 0. Constant here meaning it is independent of the frequency. That means it acts like a resistor. Now, if we change EAC 0, the value of the resistance will change. It is still independent of frequency, but it will depend on EAC 0 when EAC 0 is large. When EAC 0 is vanishingly small, very small, then that ZF that I calculate here will be independent of EAC 0, which means these are cancelling out, it is just going to be a simple resistor. So, this aligns with what we expect to see. When EAC 0 is large, the impedance is going to depend on the EAC 0 value. When it is small, the impedance value is independent of the EAC 0 value. So, basically if I model it as a parallel combination of double layer capacitance and a Faradaic impedance, I will get ZF. ZF here is a function of EAC 0 when EAC 0 is large. ZF here is just a simple resistance, constant resistance when EAC 0 is small. When it is large, it is still a resistance, but it depends on EAC 0. Okay. Now, if you look at higher harmonics, I can look at 2 omega, I can look at 3 omega, they are also fixed numbers, meaning if you look at the coefficient of 2 omega t, this is independent of omega, the coefficient of this is independent of omega, the phase difference here is 90 degree, cosine and sine are off by 90 degree. So, nth harmonic current, if you plot it in Bode plot, if I say I n omega from low frequency to high frequency, it is going to be a constant. If you look at the phase value, it is going to be 0 for odd harmonic, it is going to be 90 degree for even harmonic. Okay. So, we got analytical expression here because we are able to expand exponential of a sin theta in Fourier series. Most of the cases we will not be able to get analytical expression. So, you have few choices. One, write in Taylor series, expand up to some terms, instead of linearizing or instead of writing only up to the first frequency term, we can write for few more terms and then truncate it and then rearrange. That is one possibility. Second, in many cases you can also write an approximate Fourier series. This was published in 1997 by Professor David Harrington in Department of Chemistry, University of Victoria in Canada. I had taken the image from the website. So, for large amplitude perturbation, he has shown how to calculate it for a few reactions, including reaction with adsorbed intermediates, for the response at fundamental, for the response at second harmonic. You can use numerical method. So, we have done some research on that. So, I will describe how you can use numerical method to handle situations where we do not know how to get analytical expression. So, if you want to look at the example of Taylor series analysis here, potential of course is EDC plus EAC, where EAC can be considered as a small number, it can be a large number also. When you write this in Taylor series, we want to write current as a function of potential. Potential at x 0 plus h, where x 0 you can replace by EDC, h you can replace by EAC. Now, we would write in Taylor series as f of x 0 plus derivative, first order derivative multiplied by h, second order derivative multiplied by h square by 2 factorial and so on. And in this case, we are going to write it as f at EDC, f prime at EDC, f double prime, second derivative at EDC, correspondingly EAC, EAC square and so on. And then we are going to truncate after certain terms. So, when you write this, in case we did not know how to write this exponential of sin theta, we know of course that we can write the exponential of sin theta as Fourier series with modified Bessel functions as coefficients, but in case we did not know, we can still write it as sin theta, sin square theta, sin cube theta and so on, and truncate it after certain number of terms. In this case, truncate it after 3 terms and then rearrange it, use power law, write it in Fourier series for sin square, sin cube etc., and then rearrange it. Since we have done this example before, I will go through it little fast. Okay. So, we know that the coefficient, constant coefficient will get terms from sin square, sin cube will give sin theta and sin 3 theta, sin power 4 will give constant coefficient and sin 2 theta actually cosine, but it is all right, sin 2 theta with phase, sin 4 theta. Okay. So, if you look here, constant term can be written as 1 plus AC 0 square plus AC 0 power 4 etcetera etcetera, and similarly for the reverse reaction. Response at fundamental, response at sin omega t can be written as AC power 1, AC power 3, AC power 5 and so on. Response at 2 omega t can be written as AC square, AC power 4, AC power 6 and so on, and 3 omega t of course as cube plus AC power 5 plus AC power 7 and so on. Now, if you look at it, if EAC 0 is small or moderate, I can say this is roughly 1, this is roughly proportional to EAC 0, this is roughly proportional to EAC square, this is roughly proportional to EAC cube. That is why if I take the Fourier component at n omega, at sin omega, sin 2 omega, sin 3 omega, sin n omega, at small and moderate values it is going to be EAC 0 power n. When you go to larger amplitude, I can't neglect this, I can't neglect the further terms. So, it will not be always proportional to EAC power n, only at small and moderate values it is going to be proportional to that, at higher values it is going to be dependent. In this example, for this reaction it is going to be dependent as described by the modified Bessel function. For other reactions, the dependence is hard to get because we do not have an analytical expression. So, this is just to re-emphasize the Taylor series expansion, truncating after n terms and then rearranging will approximate the Fourier series results. I will also describe how we can do numerical simulation for this. It is not necessary to do numerical simulation for this, but if we learn how to do the numerical simulation for this, later when we go to other examples where numerical simulation is the only way or probably the easiest way, then it will be easy to follow how to do this. Okay. So, we know the expression for Faraday current here. So, numerical simulations what we do is the following. We first write the time domain expression for the current and apply sinusoidal potential. So, we say generate the sinusoidal potential as a function of time, meaning we have a series of time and correspondingly we have series of potential values. So, we have a time going from 0, 1 millisecond, 2 millisecond, 3 millisecond and so on. Correspondingly, we have potential starting at some value and then changing as given by the sinusoidal equation, and then calculate the current as a function of time and then subject this to Fourier transform and get the Fourier series coefficients. Okay. We can record the values at DC, we can record the values at fundamental, second harmonic and so on. Once you know the response at fundamental, you can calculate the impedance. Once you know the response at any other harmonic, you can plot that in Bode plot, the current response in Bode plot. Okay. This was published in 2011 by our group. This is an example with a simplified version of the reaction. Instead of taking Fe2 plus going to Fe3 plus with an electron release, we have taken a simpler equation where metal dissolves into the solution, reverse reaction is neglected. So, for certain value of the rate constant and certain value of the exponent Bf are given by B1 here at a DC bias of 0.4 voltage with an assumed capacitance, double layer capacitance of 10 microfarad per square centimeter for different AC perturbations, right. 5 millivolt and 10 millivolt give you more or less the same spectrum. So, 5 millivolt results are given at blue squares, 10 millivolt results are given as green triangle, and you can't really distinguish between them because they pretty much overlap. If we increase the amplitude to 100 millivolt, the spectrum will still be a semicircle, but the charge transfer resistance is going to be less. If we increase this to 200 millivolt, it is given by the black color circles here, charge transfer resistance decreases a lot. So, it is still modeled by a double layer capacitance with the charge transfer resistance, but this is a much smaller value compared to what we got in 5 millivolt or 10 millivolt perturbation. So, essentially what is done is we got a time, we calculate the potential using the first expression, we calculate the current using the second expression current, and then we subject this to Fourier transform. So, in summary, we can write the current results in Fourier transform because here we know how to get the analytical expression. We can use modified Bessel functions. So, it is possible to get a analytical expression for impedance, nonlinear impedance. It is also possible to get analytical expression for the current response at any frequency, second harmonic, third harmonic, and so on. In other reactions, it may be possible to use approximate Fourier series. You can refer to the publication by Professor David Harrington. In some cases, you can also expand in Taylor series and rearrange, but when you do that, you have to be very careful, because when you expand to many number of terms, the chances of mistake become more. Okay. You can also use numerical method. Numerical method has some advantages and disadvantages, but after describing it for a few examples, I will discuss with you on what are the advantages and disadvantages. You can apply it for a variety of reactions. It is possible to analyze a variety of reactions using numerical method. It is not that easy to generate Fourier series or Taylor series expansion and get accurate values for all reactions.